In mathematics, the LP spaces are function spaces defined using a natural generalization of the P-norm for finite-dimensional vector spaces. They are sometimes called Lebesgue spaces, named after Henry Lebesgue, Dunford and Schwartz 1958, 3.3, although according to the Bourbaki group Bourbaki 1987, they were first introduced by Frigais-Riesz 1910. LP spaces form an important class of Banach spaces in functional analysis, and of topological vector spaces. Because of their key role in the mathematical analysis of measure and probability spaces, Lebesgue spaces are used also in the theoretical discussion of problems in physics, statistics, finance, engineering, and other disciplines. Topic: Applications. Topic: Statistics. In statistics, measures of central tendency and statistical dispersion, such as the mean, median, and standard deviation, are defined in terms of LP metrics, and measures of central tendency can be characterized as solutions to variational problems. In penalized regression, L1 penalty and L2 penalty refer to penalizing either the L1 norm of a solution's vector of parameter values, i.e. the sum of its absolute values, or its L2 norm, its Euclidean length. Techniques which use an L1 penalty, like lasso, encourage solutions where many parameters are zero. Techniques which use an L2 penalty, like ridge regression, encourage solutions where most parameter values are small. Elastic net regularization uses a penalty term that is a combination of the L1 norm and the L2 norm of the parameter vector. Hausdorff-Young inequality. The Fourier transform for the real line, or, for periodic functions, see Fourier series, maps LP R to LQ R, or LP T to Q respectively, where 1p2 and 1p plus 1 q equals 1. This is a consequence of the Riesch-Thoren interpolation theorem, and is made precise with the Hausdorff-Young inequality. By contrast, if p greater than 2, the Fourier transform does not map into LQ. Hilbert spaces. Hilbert spaces are central to many applications, from quantum mechanics to stochastic calculus. The spaces L2 and 2 are both Hilbert spaces. In fact, by choosing a Hilbert basis, i.e., a maximal orthonormal subset of L2 or any Hilbert space, one sees that all Hilbert spaces are isometric to 2 E, where E is a set with an appropriate cardinality. The P-norm in finite dimensions. The length of a vector x equals x1, x2, xn in the n-dimensional real vector space Rn is usually given by the Euclidean norm x2 equals x1 2 plus x2 2 plus x n 2 1 2. Display style left x right underscore 2 equals left x underscore 1 caret 2 plus x underscore 2 caret 2 plus dotsb plus x underscore n caret 2 right caret 1/2. The Euclidean distance between 2 points x and y is the length x minus y2 of the straight line between the 2 points. In many situations, the Euclidean distance is insufficient for capturing the actual distances in a given space. An analogy to this is suggested by taxi drivers in a grid street plan who should measure distance not in terms of the length of the straight line to their destination, but in terms of the rectilinear distance, which takes into account that streets are either orthogonal or parallel to each other. The class of P-norms generalizes these two examples and has an abundance of applications in many parts of mathematics, physics, and computer science. Definition. For a real number P1, the P-norm or LP norm of X is defined by X P equals X1 P plus X2 P plus X n P 1 P display style left x right underscore p equals left x underscore 1 caret p plus x underscore 2 caret p plus dotsb plus x underscore n caret p right caret 1 p. The absolute value bars are unnecessary when p is a rational number and, in reduced form, has an even numerator. The Euclidean norm from above falls into this class and is the 2 norm, and the 1 norm is the norm that corresponds to the rectilinear distance. The L infinity norm or maximum norm or uniform norm is the limit of the LP norms for p infinity display style p right arrow inf t. It turns out that this limit is equivalent to the following definition: x infinity equals max x 1 x 2 x n. Display style left x right underscore inf t equals max left x underscore 1 x underscore 2 dotsc x underscore n right. CL infinity. For all p1, the p norms and maximum norm as defined above indeed satisfy the properties of a length function or norm, which are that only the zero vector has zero length. The length of the vector is positive homogeneous with respect to multiplication by a scalar, positive homogeneity, and the length of the sum of two vectors is no larger than the sum of lengths of the vectors, triangle inequality. Abstractly speaking, this means that Rn together with the p norm is a Banach space. This Banach space is the LP space over Rn. Topic: relations between p norms. The grid distance or rectilinear distance, sometimes called the Manhattan distance between 2 points, is never shorter than the length of the line segment between them, the Euclidean or, as the crow flies, distance. Formally, this means that the Euclidean norm of any vector is bounded by its one norm, x2 x1. Display style left x right underscore 2 leq left x right underscore 1. This fact generalizes to p norms in that the p norm x p of any given vector x does not grow with p x p plus a x p for any vector x and real numbers p1 and a 0. In fact, this remains true for 0 x1 and x2. Display style left x right underscore 1 leq squint n left x right underscore 2. This inequality depends on the dimension n of the underlying vector space and follows directly from the Cauchy-Schwarz inequality. In general, for vectors in Cn where 0 x p x Rn 1 r minus 1 p x p. Display style left x right underscore p leq left x right underscore r leq n caret 1 r 1 p left x right underscore p. When 0 in Rn for n greater than 1, the formula xp equals x1 p plus x2 p plus plus xn p 1 p. Display style x underscore p equals left x underscore 1 caret p plus x underscore 2 caret p plus cdots plus x underscore n caret p right caret 1 p defines an absolutely homogeneous function for 0. On the other hand, the formula x 1 p plus x 2 p plus x n p. Display style x underscore 1 caret p plus x underscore 2 caret p plus dotsb plus x underscore n caret p defines a subadditive function at the cost of losing absolute homogeneity. It does define an F norm, though, which is homogeneous at degree p. Hence, the function d p x y equals I equals 1 n x I minus y I p. Display style d underscore p x y equals sum underscore I equals 1 caret n x underscore I y underscore I caret p defines a metric. The metric space Rn dp is denoted by np. Although the p-unit ball Bnp around the origin in this metric is concave, the topology defined on Rn by the metric dp is the usual vector space topology of Rn, hence Np is a locally convex topological vector space. Beyond this qualitative statement, a quantitative way to measure the lack of convexity of Np is to denote by Cp n the smallest constant C such that the multiple Cbnp of the p-unit ball contains the convex hull of Bnp, equal to Bn1.
The fact that for fixed PCP n equals n1 p minus 1 infinity, as n infinity display style c underscore p n equals n caret 1 p1 to inf t q quad text as n to inf t shows that the infinite dimensional sequence space P defined below is no longer locally convex. Topic: When P equals 0. There is one zero norm and another function called the zero norm
with quotation marks. The mathematical definition of the zero norm was established by Banach's theory of linear operations. The space of sequences has a complete metric topology provided by the F norm x n n 2 minus n x n 1 plus x n display style x underscore n mapsto sum underscore n 2 caret n frac x underscore n 1 plus x underscore n, which is discussed by Stefan Rolevich in metric linear spaces. The zero norm space is studied in functional analysis, probability theory, and harmonic analysis. Another function was called the zero norm by David Donahoe, whose quotation marks warn that this function is not a proper norm, is the number of non-zero entries of the vector x. For example, scaling the vector x by a positive constant does not change the norm. Many authors abuse terminology by omitting the quotation marks. Defining 00 equals 0, the zero norm of x is equal to x 1 0 plus x 2 0 plus x n 0. Display style x underscore 1 caret 0 plus x underscore 2 caret 0 plus cdots plus x underscore n caret 0. This is not a norm because it is not homogeneous. Despite these defects as a mathematical norm, the non-zero counting norm has uses in scientific computing, information theory, and statistics, notably in compressed sensing in signal processing and computational harmonic analysis. The P-norm in countably infinite dimensions and P-spaces. The P-norm can be extended to vectors that have an infinite number of components, which yields the space P. This contains as special cases 1. The space of sequences whose series is absolutely convergent. 2. The space of square summable sequences, which is a Hilbert space, and infinity, the space of bounded sequences. The space of sequences has a natural vector space structure by applying addition and scalar multiplication coordinate by coordinate. Explicitly, the vector sum and the scalar action for infinite sequences of real or complex numbers are given by x 1 x 2 x n x n plus 1 plus y 1 y 2 y n y n plus 1 equals x 1 plus y 1 x 2 plus y 2 x n plus y n x n plus 1 plus y n plus 1 lambda x 1 x 2 x n x n plus 1 equals lambda x 1 lambda x2 lambda xn plus 1. display style begin aligned and x_1 x_2 L dots x_n x_n plus 1 L dots plus y_1 y_2 L dots y_n y_n plus 1 L dots equals and x_1 plus y_1 x_2 plus y_2 L dots x_n plus y_n x_n plus 1 plus y_n plus 1 L dots 6 pt and lambda cdot left x_1 x_2 L dots x_n x_n plus 1 L dots right equals and lambda x_1 lambda x_2 L dots lambda x_n lambda x_n plus 1 L dots. End aligned. Define the p-norm. Xp equals x1 p plus x2 p plus plus xn p plus xn plus 1 p plus 1 p. Display style left x right underscore p equals left x_1 caret p plus x_2 caret p plus cdots plus x_n caret p plus x_n plus 1 caret p plus cdots right caret 1 p. Here, a complication arises, namely that the series on the right is not always convergent. So, for example, the sequence made up of only ones, 1, 1, 1, will have an infinite p-norm for 1p. One can check that as p increases, the set p grows larger.
For example, the sequence 1, 1, 2, 1, n, 1, n, plus 1. Display style left 1 frac 1 2 L dots frac 1 n frac 1 n plus 1 L dots right is not in 1, but it is in P for p greater than 1, as the series 1 p plus 1 2 p plus 1 n p plus 1 n plus 1 p plus display style 1 caret p plus frac 1 2 caret p plus cdots plus frac 1 n caret p plus frac 1 n plus 1 caret p plus cdots diverges for p equals 1, the harmonic series, but is convergent for p greater than 1.
One also defines the infinity norm using the supremum x infinity equals sup x 1 x 2 x n x n plus 1. Display style left x right underscore inf t equals sub x underscore 1 x underscore 2 dotsc x underscore n plus 1 L dots and the corresponding space infinity of all bounded sequences. It turns out that x infinity equals lim p infinity x p display style left x right underscore inf t equals lim underscore p to inf t left x right underscore p if the right hand side is finite or the left hand side is infinite. Thus, we will consider p spaces for 1p infinity. The p-norm thus defined on P is indeed a norm, and P together with this norm is a Banach space. The fully general LP space is obtained, as seen below, by considering vectors, not only with finitely or countably infinitely many components, but with arbitrarily many components. In other words, functions. An integral instead of a sum is used to define the p-norm. LP spaces. An LP space may be defined as a space of functions for which the pth power of the absolute value is Lebesgue integrable, where functions which agree almost everywhere are identified. More generally, let 1p f p s f p d mu 1p infinity display style f underscore p equivalent left int underscore s f caret p mathrm d mu right caret 1p. The set of such functions forms a vector space with the following natural operations: f plus g x equals f x plus g x lambda f x equals lambda f x display style begin aligned f plus g x and equals f x plus g x lambda f x and equals lambda f x end aligned for every scalar lambda. That the sum of two pth power integrable functions is again pth power integrable follows from the inequality f plus g p p 2 p minus 1 f P plus G P display style F plus G underscore P caret P LEQ2 caret P1 left F underscore P caret P plus G underscore P caret P right. This comes from the convexity of T P display style T mapsto T caret P for P1 display style P GEQ1. In fact, more is true. Minkowski's inequality says the triangle inequality holds for P. Thus the set of pth power integrable functions, together with the function P, is a seminormed vector space, which is denoted by L P S mu. Display style mathcal L caret P S mu. This can be made into a normed vector space in a standard way. One simply takes the quotient space with respect to the kernel of P.
Since for any measurable function f, we have that f p.
Topic 0 If and only if f0 almost everywhere, the kernel of P does not depend upon P n f equals 0 mu almost everywhere equals ker P 1 P infinity display style mathcal n equivalent f equals 0 mu text almost everywhere equals ker CDOT underscore P q quad for 1 LEQ P in the quotient space. Two functions f and g are identified if f equals g almost everywhere. The resulting normed vector space is, by definition, LP S mu LP S mu n display style L caret P S mu equivalent mathcal L caret P S mu mathcal n for P equals infinity. The space L infinity S mu is defined as follows. We start with the set of all measurable functions from S to C or R which are bounded. Again, two such functions are identified if they are equal almost everywhere. Denote this set by L infinity S mu. For a function f in this set, the essential supremum of its absolute value serves as an appropriate norm f infinity inf c0 f x c for almost every x. Display style f underscore inf t equivalent inf c geq0 f x leq c text for almost every x as before. If there exists q f infinity equals lim p infinity fp. Display style f underscore inf t equals lim underscore p to inf t f underscore p for 1 p infinity LP S mu is a Banach space. The fact that LP is complete is often referred to as the Riesch-Fischer theorem. Completeness can be checked using the convergence theorems for Lebesgue integrals. When the underlying measure space S is understood, LP S mu is often abbreviated LP mu or just LP. The above definitions generalize to Bochner spaces.
Topic: Special cases.
Similar to the P spaces, L2 is the only Hilbert space among LP spaces. In the complex case, the inner product on L2 is defined by f g equals s f x g x d mu x. Display style Langle f g wrangle equals int underscore s f x overline g x mathrm d mu x. The additional inner product structure allows for a richer theory, with applications to, for instance, Fourier series and quantum mechanics. Functions in L2 are sometimes called quadratically integrable functions, square integrable functions or square summable functions, but sometimes these terms are reserved for functions that are square integrable in some other sense, such as in the sense of a Riemann integral Titchmarsh 1976. If we use complex-valued functions, the space L infinity is a commutative C** algebra with pointwise multiplication and conjugation. For many measure spaces, including all sigma finite ones, it is in fact a commutative von Neumann algebra. An element of L infinity defines a bounded operator on any LP space by multiplication.
For 1p infinity, the P spaces are a special case of LP spaces, when S equals n, and mu is the counting measure on n. More generally, if one considers any set S with the counting measure, the resulting LP space is denoted P S. For example, the space P Z is the space of all sequences indexed by the integers, and when defining the P norm on such a space, one sums over all the integers. The space P n, where n is the set with n elements, is Rn with its P norm as defined above. As any Hilbert space, every space L2 is linearly isometric to a suitable 2 I, where the cardinality of the set I is the cardinality of an arbitrary Hilbertian basis for this particular L2. Topic: Properties of LP spaces. Equals. Topic: Dual spaces.
The dual space, the Banach space of all continuous linear functionals of LP mu for 1 i.e. q equals pp-1 display style q equals tfrac p p1. This isomorphism associates G element of LQ mu with the functional kappa p G element of LP mu defined by f kappa p G f equals FGD mu display style f mapsto kappa underscore p G f equals int FG mathrm D mu for every f element of LP mu display style f in L caret p mu. The fact that kappa p G is well defined and continuous follows from Holder's inequality. Kappa p LQ mu LP mu is a linear mapping which is an isometry by the extremal case of Holder's inequality. It is also possible to show, for example with the Radon-Nikodym theorem, c that any G element of LP mu can be expressed this way, i.e., that kappa p is onto. Since kappa p is onto an isometric, it is an isomorphism of Banach spaces. With this isometric isomorphism in mind, it is usual to say simply that LQ is the dual Banach space of LP. For 1. Consider the map from LP mu to LP mu obtained by composing kappa q with the transpose or adjoint are the inverse of kappa p J p L p mu kappa q L q mu kappa p minus 1 L p mu display style J underscore P L caret P mu overset kappa underscore Q long right arrow L caret Q mu caret asterisk overset left kappa underscore P caret minus 1 right caret asterisk long right arrow L caret P mu caret asterisk asterisk. This map coincides with the canonical embedding J of LP mu into its bidual. Moreover, the map JP is onto as composition of two onto isometries, and this proves reflexivity. If the measure mu on S is sigma finite, then the dual of L1 mu is isometrically isomorphic to L infinity mu. More precisely, the map kappa 1 corresponding to P equals 1 is an isometry from L infinity mu onto L1 mu. The dual of L infinity is subtler. Elements of L infinity mu can be identified with bounded sign finitely additive measures on S that are absolutely continuous with respect to mu. See bar space for more details. If we assume the axiom of choice, this space is much bigger than L1 mu except in some trivial cases. However, Sahar and Scheller proved that there are relatively consistent extensions of Zermelo-Frankel set theory ZF plus DC plus.
Every subset of the real numbers has the bare property, in which the dual of infinity is 1.
Embeddings. Colloquially, if 1p LQ S mu LP S mu IFFS does not contain sets of finite but arbitrarily large measure, and LP S mu LQ S mu IFFS does not contain sets of non-zero but arbitrarily small measure, neither condition holds for the real line with the Lebesgue measure. In both cases the embedding is continuous, in that the identity operator is a bounded linear map from LQ to LP in the first case, and LP to LQ in the second. This is a consequence of the closed graph theorem and properties of LP spaces. Indeed, if the domain S has finite measure, one can make the following explicit calculation using Holder's inequality: 1 fp1 1 q q minus p fpq p display style math bf 1 f caret p underscore 1 leq math bf 1 underscore q qp f caret p underscore q p leading to fp mu s 1 p minus 1 qfq display style f underscore p leq mu s caret 1 P1 Q F underscore Q.
The constant appearing in the above inequality is optimal, in the sense that the operator norm of the identity I LQ S mu LP S mu is precisely I Q P equals mu S 1 P minus 1 Q. Display style I underscore Q P equals mu S caret 1 P1 Q. The case of equality being achieved exactly when F equals 1 mu A E equals.
Dense subspaces equals. Throughout this section we assume that 1p let S sigma mu be a measure space. An integrable simple function f on S is one of the form f equals j equals 1 naj 1 aj display style f equals sum underscore j equals 1 caret n a underscore j math bf 1 underscore r underscore j, where aj is scalar. Aj element of sigma has finite measure, and 1 aj display style math bf 1 underscore a underscore j is the indicator function of the set aj display style a underscore j for j equals 1 n. By construction of the integral, the vector space of integrable simple functions is dense in LP S sigma mu. More can be said when S is a normal topological space and sigma its Borel sigma algebra, i.e., the smallest sigma algebra of subsets of S containing the open sets. Suppose Vs is an open set with mu v. It can be proved that for every Borel set an element of sigma contained in V, and for every epsilon greater than 0, there exists a closed set F and an open set U such that FAU V and mu U minus mu F equals mu UF epsilon display style F subset A subset U subset B quad text and quad mu U mu F equals mu U segment F. It follows that there exists a continuous Urisan function 0 phi 1 display style 0 LEQ phi LEQ 1 on S display style S that is 1 display style 1 on F display style f and 0 display style 0 on su display style s segments u with s 1 or minus phi d mu epsilon display style int underscore s math bf 1 underscore a phi mathrm d mu. If s can be covered by an increasing sequence vn of open sets that have finite measure, then the space of p integrable continuous functions is dense in LP s sigma mu. More precisely, one can use bounded continuous functions that vanish outside one of the open sets vn.
This applies in particular when S Rho and when mu is the Lebesgue measure. The space of continuous and compactly supported functions is dense in LP Rho. Similarly, the space of integrable step functions is dense in LP Rho. This space is the linear span of indicator functions of bounded intervals when d
1 are bounded rectangles when d equals 2 or more, generally of products of bounded intervals. Several properties of general functions in LP Rho are first proved for continuous and compactly supported functions, sometimes for step functions, then extended by density to all functions. For example, it is proved this way that translations are continuous on LP Rho in the following sense: f element of L P R D tau T F minus F P 0 as R D T 0 display style forl f in L caret P math BF R caret D Q quad left tau underscore T FF right underscore P to 0 quad text as math BF R caret D ni T to 0 where tau T F X equals F X minus T display style tau underscore T F X equals F X T.
Topic LP 0 let S sigma mu be a measure space. If 0 NP F equals S F P D mu infinity. Display style n underscore P F equals int underscore S F caret P D mu as before. We may introduce the P norm F P equals NP F 1 P, but P does not satisfy the triangle inequality in this case, and defines only a quasi-norm. The inequality A plus B PAP plus BP, valid for A, B0 implies that Rudin 1991, section 1.47 NP F plus G NP F plus NP G displaystyle n underscore P F plus G LEQ n underscore P F plus n underscore P G, and so the function dP F G equals NP F minus G equals F minus G PP displaystyle D underscore P F G equals n underscore P F G equals F G underscore P caret P is a metric on LP mu. The resulting metric space is complete. The verification is similar to the familiar case when P1.
In this setting, LP satisfies a reverse Minkowski inequality, that is for U V in LP U plus V P U P plus VP display style U plus V underscore P GEQ U underscore P plus V underscore P. This result may be used to prove Clarkson's inequalities, which are in turn used to establish the uniform convexity of the spaces LP for 1. The space LP for 0, the only non-empty convex open set in LP 0, 1 is the entire space. Rudin 1991, section 1.47. As a particular consequence, there are no non-zero linear functionals on LP 0, 1. The dual space is the zero space. In the case of the counting measure on the natural numbers producing the sequence space LP mu equals p, the bounded linear functionals on P are exactly those that are bounded on 1, namely those given by sequences in infinity. Although P does contain non-trivial convex open sets, it fails to have enough of them to give a base for the topology. The situation of having no linear functionals is highly undesirable for the purposes of doing analysis. In the case of the Lebesgue measure on Rn, rather than work with LP for 0. L0, the space of measurable functions. The vector space of equivalence classes of measurable functions on S sigma mu is denoted L0 S sigma mu. Calton, Peck and Roberts 1984. By definition, it contains all the LP and is equipped with the topology of convergence in measure. When mu is a probability measure, i.e., mu S equals 1, this mode of convergence is named convergence in probability. The description is easier when mu is finite. If mu is a finite measure on S sigma, the zero function admits for the convergence in measure the following fundamental system of neighborhoods: V epsilon equals F mu x F x greater than epsilon epsilon greater than 0. Display style V underscore var epsilon equals BIGL F mu BIGL x F x greater than var epsilon big R 0. The topology can be defined by any metric D of the form D F G equals S phi F x minus G x D mu x. Display style D F G equals int underscore S varphi BIGL F x G x big R mathrm D mu x, where phi is bounded continuous concave and non-decreasing on 0 infinity with phi 0.
Topic 0 and phi t greater than 0 when t greater than 0. For example, phi t min t 1. Such a metric is called Levy metric for L0. Under this metric, the space L0 is complete. It is again an F space. The space L0 is in general not locally bounded and not locally convex. For the infinite Lebesgue measure lambda on Rn, the definition of the fundamental system of neighborhoods could be modified as follows: W epsilon equals F lambda x F x greater than epsilon and x 1 epsilon epsilon. Display style W underscore var epsilon equals left F lambda left x F x greater than var epsilon text and x. The resulting space L0 Rn lambda coincides as topological vector space with L0 Rn G x d lambda x for any positive lambda integrable density G. Weak LP. Let S sigma mu be a measure space, and F a measurable function with real or complex values on S. The distribution function of F is defined for t greater than 0 by lambda F t equals mu x element of S F x greater than t. Display style lambda underscore F t equals mu left x in S F x greater than t right. If F is in LP S mu for some p with 1 p lambda F t F p p t p. Display style lambda underscore F t leq frac F underscore p caret p t caret p. A function F is said to be in the space weak LP S mu or LP W S mu if there is a constant c greater than 0 such that, for all t greater than 0, lambda f t cpt
p display style lambda underscore f t leq frac c caret p t caret p. The best constant c for this inequality is the LP W norm of F and is denoted by F p W equals sup t greater than 0 t lambda f 1 p t. Display style F underscore P W equals sup underscore t greater than 0 tilde t lambda underscore F caret 1 P t. The weak LP coincide with the Lorentz spaces LP infinity, so this notation is also used to denote them. The LP W norm is not a true norm, since the triangle inequality fails to hold. Nevertheless, for F in LP S mu F P W F P display style F underscore P W leq F underscore P, and in particular LP S mu LP W S mu. In fact, one has F L P P equals F x P D mu x F x greater than T P plus F X T F P mu F greater than T display style F underscore L caret P equals int F X caret P D mu X GEQ int underscore F X greater than T caret P plus int underscore F X LEQT F caret P GEQT caret P mu F greater than T and raising to power 1 P display style 1 P and taking the supremum in T display style T. One has F L P sup T greater than 0 T mu F greater than T 1 P equals F L P W display style F underscore L caret P GEQ sup underscore T greater than 0 T mu F greater than T caret 1 P equals F underscore L caret P W. Under the convention that two functions are equal if they are equal mu almost everywhere, then the spaces LP W are complete. Graphicos 2004.
For any 0 f LP infinity equals sup 0 mu e infinity mu e minus 1 r plus 1 p e f r d mu 1 r display style f underscore L caret p inf t equals sup underscore 0 is comparable to the LP W norm. Further, in the case p greater than 1, this expression defines a norm if r equals 1. Hence, for p greater than 1, the weak LP spaces are Banach spaces. Graphicos 2004. A major result that uses the L2 spaces is the Marcinkiewicz interpolation theorem, which has broad applications to harmonic analysis and the study of singular integrals. Topic: Weighted LP spaces.
As before, consider a measured space S sigma mu. Let W S 0 infinity be a measurable function. The W-weighted LP space is defined as LP S W d mu, where W d mu means the measure nu defined by nu a W x d mu x a element of sigma. Display style nu a equivalent int underscore a W x mathrm d mu x q quad a in sigma. Or, in terms of the radon-nicotin derivative, W equals d mu. The norm for LP S W d mu is explicitly U L P S W d mu S W x U x P d mu x 1 P display style U underscore L caret P S W mathrm D mu equivalent left int underscore S W x U x caret P mathrm D mu x right caret 1 P. As LP spaces, the weighted spaces have nothing special, since LP S W d mu is equal to LP S d nu.
But they are the natural framework for several results in harmonic analysis. Graphicos 2004. They appear, for example, in the Muckenhout theorem for 1. Topic: LP spaces on manifolds. One may also define spaces LP M on a manifold, called the intrinsic LP spaces of the manifold, using densities. Topic: See also. Notes